let's look at an example problem of a work rate problem. So as I read this, we're told that a water tank on a farm in Texas can be filled with a large inlet pipe and a small inlet pipe in 3 hours. The large inlet pipe alone can fill the tank in 2 hours less time than the small inlet pipe alone. Find the time to the nearest tenth of an hour that each pipe can fill the tank alone. So, before we even get into this problem, I do want to talk about a common sense estimate so that we can get a ballpark idea of roughly what our answer should be. So what I like to start with is I like to start off with saying, what if they had equal speed or equal rate? So if they had equal speed or equal rate, and it took them 3 hours together, then each one would be 6. So what some people do is they say that it's 1.5 for each, but that wouldn't make any sense. We got to think about the fact that if they're working alone, so that's what we're looking for here, is we're looking for their time alone. So if we are looking at their time alone, it's got to be more than when they're working together, not less. It wouldn't make sense that alone they can do it even quicker. Now, that's our start to our common sense estimate. That's not actually going to be our common sense estimate, because we're going to say, well, the large one is faster. It's taking less time. So it's going to be a little less than 6 for the large inlet pipe. But that means that the small one needs to be even more. So maybe 5 and 7, something along those lines, because that is a 2-hour difference, but the large one can do it quicker. So that's the way that I would kind of get a ballpark estimate, is to say, well, what if they were filling it at the same rate? What if they worked at the same speed? How long would it take each one of them alone? And then look at the fact that, okay, well, the large one takes less time, so let's drop that number a little bit, make the other one a little bit bigger. Gets you a ballpark estimate just to see if our actual answer ends up working. Now we know that in order to solve this problem, we're going to use the formula 1 over the time of one of them alone. We'll go ahead and say big, plus 1 over the time of the other one alone, we'll call it small, equals 1 over their time together. We know that's the underlying formula for this problem, which means I need to figure out either values or variables for the time that it takes the big one alone, the time that it takes the small one alone, and their time together. Now their time together is straight up given to us as 3 hours. Now as far as the other values, we know that the large inlet pipe can fill the tank in 2 hours less time. So if we call the small one x, then the big one is 2 hours less than that. So it's x minus 2. So now we can plug those values into our formula to say we have 1 over x minus 2 plus 1 over x equals 1 over 3. This looks to me like a rational equation, an equation with fractions in it. And as you know, fractions suck, so get rid of the fractions. We're going to multiply both sides of the equation by the LCD. So that means we're going to put the LCD into the top of every fraction. Again, not the bottom. We're just putting it in the top because our goal is to get rid of the bottom, to get rid of the fractions. So in the first fraction, the x minus 2's divide out, leaving just the 3x. In the second fraction, the x's divide out. As I distribute the 3, I get 3x minus 6. And on the right side, the 3's divide out. And if I distribute the x, I get x squared minus 2x. I can combine like terms on the left, and then bring everything over to the right. So I have this quadratic equation to solve. Now this quadratic equation is not factorable, so I am going to have to use the quadratic formula. I go ahead and use the trick, even though we're probably going to use a calculator anyhow because we want to get some sort of decimal answer. It usually makes more sense on word problems. It wouldn't make sense on a word problem to say it takes square root of 2 hours. You actually want to put it in the calculator and give a more reasonable answer. So I divide both sides by 2 so that my a value is 1/2, my b value is -4, and my c value is 3. And I plug into the quadratic formula of the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Let's do some simplifying now. We'll do the calculator in a second, but I think that if we plug as little into the calculator as possible, we're less likely to type stuff wrong. So I've got 4 times 1/2 is 2, 2 times 3 is 6, and in my bottom, 2 times 1/2 is 1. And this is why I wanted to use the trick on this problem. It's really going to make it easier to plug in. So I'm going to plug two things in my calculator. I'm going to plug in 4 plus the square root of 10, and I'm going to plug in 4 minus the square root of 10. So off screen, I'm going to grab my calculator because these are not hard things to plug in the calculator, so I don't think you need to actually see this calculation. When I do 4 plus the square root of 10, I'm getting about 7.2. When I do 4 minus the square root of 10, I'm getting about 0.8. Let's go back up to how we defined each of these values. So remember 7.2 and 0.8 were the two values that I got. So x was the time for the small pipe alone. Let's look at our estimates, 5 and 7. We estimated 7 as our ballpark figure. One of our answers is close to that. One is not. Let's look at why that's the case. Let's look at what happens if I let x equal 7.2 versus what happens if I let x equal 0.8. The time of the big guy, if x is 7.2, would be 2 less than that, or 5.2. If I let it be 0.8, 2 less than that, well, 0.8 minus 2 is -1.2. That's not good. I can't have a negative time. So my answer of 0.8 doesn't make sense in this case. I got to throw it out. And so my large inlet pipe, or my big one, could fill this in 5.2 hours alone, and the small one could do it in 7.2 hours alone, which fits into my common sense estimate really nicely. My guess of 5 and 7 was pretty close to being dead on.